Have you ever asked yourself, can we power the whole world from the sun? What would that look like? Do we need to cover the Earth in solar panels? Let's find out.
Hi, my name is Stefan and I help companies solve problems and communicate concepts by designing and building interactive 3D applications, from product showcases to training simulations to anything in between. Today I want to create an application that can help us understand how might the world look like if we were to power it completely with solar energy. So stick around if you want to see the result. The amount of solar energy reaching Earth in 1 hour is more than enough to power the entire planet for a year. It sounds insane, but it's true. According to the International Energy Agency, the global electricity power consumption in 2022 was around 29,000 terawatt-hours. Scientists estimate that the sun hits the Earth with around 173,000 terawatts of power on average. Now, does this mean that we can just take the energy whenever we need it? Climate crisis solved? Happy ever after? Well, no. For one, we need technology that captures that potential energy and somehow converts it to electricity, which we can then use to power our houses, infrastructure, etc. For a few years now, we have photovoltaic technology that uses the sunlight's energy to convince electrons in a piece of silicon to move, which creates an electric field that we can harness. But we do not have nearly enough solar panels to capture all of the sunlight in the world everywhere. Additionally, this process is not very efficient, as with current solar panel technology, we can only capture around 23% of the potential energy. The sunlight also does not reach the Earth evenly and constantly. You might have noticed that sometimes the sun does not even seem to be present at a time we call night. And without the sun, no solar panel in the world can capture sunlight to convert it to electricity. So is it impossible? I don't know, but it's obviously challenging. Then why face this challenge? Because I think it's fun. And of course I know that we have so many more renewable energy sources that we can use to power a sustainable future, like wind, hydro or geothermal power. And ideally, the sustainable energy production of the future is made up of a combination of multiple technologies to make use of all of their strength while alleviating some of their shortcomings by spreading the load on multiple sources. But let's you and me just decide that the world has chosen to focus on solar energy for this thought experiment. Okay? Okay. Realistically, we would need a lot of infrastructure to facilitate the storage and distribution of that power. Even today, if you install solar on the roof of your house, you can use the energy produced during the day at night, using energy storage in the form of batteries. Depending on where the solar panels will be located and where the power is needed in the world, we would need some serious rebuilding of the global power grid. But since we're best buddies already, let's just say that this problem is already taken care of and we just need to find out where to place the solar panels. For the number of solar panels needed, we have to research how much power a typical panel can produce throughout a year on average and then divide the world's energy demands for a year by that number to get the number of solar panels needed. But since the solar production is dependent on where the panels are placed, this variable is hard to pin down. Also, depending on where we want to place the solar panels, we would face different problems from political to environmental to agricultural issues. So we're trying to aim for the lowest possible impact here, while still targeting regions with a potential high energy yield. For that part, I let AI help out a bit. Put in the necessary data and let it figure out possible placements for the solar panels. Here's what it came up with.
Location. Ideally, solar panels would be placed in deserts and semi-arid regions with high sun exposure and minimal land use conflicts. These areas offer high solar irradiance. More sunlight translates to higher electricity generation. Lower land use competition minimizes impact on agriculture and population centers. Area. Estimates suggest covering approximately 1.5% of the global landmass with solar panels would be sufficient. This translates to roughly 11.5 million square kilometers or 4.4 million square miles. Capacity. Based on current best efficiency panels, around 23%, this area could theoretically generate around 30,000 terawatt-hours of electricity per year. Locations for solar panels. Atacama Desert, South America. Roughly 30% of the panels could be placed here due to its exceptional solar irradiance, highest in the world, and vast, sparsely populated areas. Sahara Desert, Africa. Approximately 25% could be located here, considering its vast size and high irradiance despite some population density concerns. Australian deserts. This region, including the Grand Sandy Desert and the Gibson Desert, could accommodate around 15% of the panels due to its high solar potential and vast sparsely populated land. Gobi Desert, China and Mongolia. With high irradiance and suitable land, this region could hold roughly 10% of the panels, balancing considerations of land availability and potential environmental impact. Other deserts and semi-arid regions. The remaining 20% could be distributed across suitable locations globally, including the Kalahari Desert, Africa, Mojave Desert, North America, and Thar Desert in India, Pakistan.
Keep in mind that all of that data is based on approximate numbers and figures, so take it with a grain of salt. With the data, facts and figures out of the way, we can get to designing and building the application to visualize the data. Since this process can take a long time, a lot of work and resources, I'm going to aim for building a working app prototype that showcases the concept of the application. A proof of concept basically. I will develop it for a desktop PC platform since this is the easiest way to go for now. Let's first think about how we want to visualize the data and what building blocks we need for that. The main goal is to showcase where and how many solar panels need to be placed that produce enough energy to meet the world's electricity needs. So my thought is to start with an interactive view of the globe. Sorry to all of the potential flat Earth viewers that I might be losing at this point. This main view gives the user the possibility to navigate around the planet and see the regions where the solar panels will be placed as little UI elements pinned to the corresponding locations. Upon interacting with the region, the user will be brought into a new view that shows a 3D visualization of the area with the solar panels placed on the landscape. Additionally, I want to add information about the area covered by solar panels, the expected energy production per year for that area, and the percentage of production worldwide. Users will be able to navigate around it and get a feel for how that might look like, as well as having accompanying data to be able to contextualize it. Of course, we also need an option to get back to the main view to choose another area to look at. After the initial sketch is done, I translate it to an initial UI design pass. In this step of the process, I would normally include the CI of the company or organization this app is built for in terms of colors, logos, fonts, and wording. But since I'm building this for myself, I will keep the design simple and minimalist while still implementing modern elements. This is where I can get creative and try stuff out, always thinking of usability and also appeal. If people see the app and don't want to use it, what's the point, right? It should feel playful and fun, not overcluttered with information, but still having the necessary data front and center, so the main purpose of the application does not get lost. The plan is done, now it's time to execute. My tool of choice for creating interactive applications is the Unreal Engine. While being a game engine, it has been used for various non-game purposes throughout the years, from architectural visualization to car configurators to virtual production, filmmaking and animation. It's a really powerful piece of software with a very artist and developer-friendly approach and company behind it. I've been using it for years for the creation of 3D interactive applications of all sorts, and since I love it so much, I'm also an Unreal authorized instructor, training companies and individuals on using the Unreal Engine for their specific use cases while helping them find out if it's a good fit for them or not. Small disclaimer here. This part will not be a step-by-step Unreal Engine tutorial. There are a lot of those already here on YouTube. I'd rather show you a high-level overview of my workflow so that you can understand how I got to the end result that I will show in a few moments.
First, I need the Earth, so I use a sphere, add a light for the sun, and set up my visual settings for the scene. Then I create a material for the Earth using the textures that you can get for free from the website of the NASA organization. I set up base color, normal, and roughness, and then I build an effect for the city lights that you can see at night. I have to first find out where the sun does shine on the Earth and where it doesn't, so I build a mask for that and use that mask to drive where the city lights will be shown and where they won't be shown. Then I add an Fresnel effect for the atmosphere so that the edges of the sphere seem like they are glowing like the atmosphere. I'm going for a very minimalistic approach here and not very visually realistic so that we can save on resources and performance. Since the atmosphere feels too bright for me overall, I use the mask of the night of the Earth to drive that as well, which makes it feel a little bit more balanced. Now I start building some UI elements. I start with the content boxes that I will have at the bottom of the screen that I can drag in or drag out of the view. With the shape of the overall box set, I add the elements of the text and the image for the icons that I want to display here. Then I move over to the main UI, where I can combine all of the elements and bring it all together in one cohesive thing. Now add a bar at the bottom of the screen where I place the 3 content boxes that showcase the necessary data that I want to display here. I've prepared the content boxes so that I am able to change the content and the visuals, in this case the icons, of any of the boxes however I want to. This modular approach makes it easy to reuse elements and not having to do everything 10 times. The pop-up info box is also dynamically filled with data that I've set up in a data asset, as you can see here. And this has all of the info of where this is, how it's called, and all of the data that's necessary. I then build a script that places the hotspots on the surface of the Earth based on the real-world coordinates that I have saved in the data assets. Of course, I also need to script the interactive parts of the application. For that I use Unreal Engine's Blueprint system, which is a visual scripting system based on nodes that allows me to script any logic and interactive parts without a single line of code. And I need to playtest in between to test if everything works as expected. For building the landscapes that I want to display in the app, I use this website that you can see here on screen. And this allows me to download satellite data in the form of height maps and color maps that I can then use to generate my meshes. I then create a very high density plane where I can use the height map data to displace it so that it takes the shape of the landscape. Adding the color information and some background and some lights, I then use a tool that I created where it allows me to place splines on my landscape, and within the splines it automatically generates a grid of solar panels which then adapt to the surface of the landscape. Since all of my landscape meshes now have a very high resolution, I use a feature called Nanite that adapts the resolution of a mesh based on the distance to the camera.
Okay, let's take a look at the finished result, shall we?
I've added an intro and some transitions to the application. We start out with the view of the globe, where I have all of the interaction hotspots that I can click on to interact with them. This brings up the pop-up info box. I've added the feature so that I can make it day on the Earth wherever I'm looking at, so that I can see where I'm clicking and where the hotspots are on the Earth. Dragging from the bottom brings up my information panels that show me how much power we can produce through the year, how much landmass is covered, and so on. When I click on details on one of the pop-up info boxes, it brings me to the landscape view of that region where I can explore and see how the solar panels are placed on there. Of course, all of these are just visual examples, none of the proportions and scales are really correct here. Once I'm finished exploring and I'm happy, I can go back to the main view to select another region to check out. Here we have the Sahara Desert, for example, which also looks very cool. At the bottom of the screen here, I can see how much power will be produced per year in this region, what percentage of the overall power production it takes up, and what area is covered by solar panels. I've also visualized the Gibson Desert in Australia. It looks like this.
So, this was my attempt to answer the question, can we power the whole world from the sun? By creating a prototype application that visualizes approximate data in a clear and engaging way, I hope I could demonstrate the value of interactive 3D visualizations. Of course, we could expand the features and functionalities of the application by adding the possibility for the user to configure the placement and distribution of the solar panels themselves, visualizing the electricity storage and distribution solution, or implementing real-world satellite data for an even more realistic result. If you have any other ideas on how to improve the application, please share them in the comments. Maybe we can do a follow-up video if you like it. And if you own or work at a company or organization that could benefit from a similar application or needs consultation on deciding how to utilize real-time 3D technology in their workflow or communication approach, feel free to reach out. You'll find the contact info in the description. With that, we've reached the end of this video. If you have any ideas or wishes of other topics I should cover and build applications for, let me know by leaving a comment down below. And if you're still here, thanks for watching and consider subscribing if you want to see more videos like this. See you next time.